All right, this is lecture number 8 in the respiratory series, and the learning objective is actually fairly straightforward. And if you can remember that the punchline is always going to be that gas moves according to a pressure gradient. Oxygen will move according to a pressure gradient. If you can remember that, we're going to be in good shape. So what you want to be able to do is describe the PO2, partial pressure of oxygen, of inspired air, alveoli, pulmonary capillaries at the venous end, pulmonary veins, systemic arteries, capillaries at both the arterial and venous ends, as well as at the tissues and the systemic veins. I know it seems like a lot, but I promise you it's really not that much. Now, I've already given you a preview into this. This is really going to be what is essentially the master slide for this particular lecture. So here it is. Two things that you need to pay actually, can we just ignore this box for right now? Let me get back to that in just a second. All right. So what do we have here? We now have, there's the heart, of course, right? The right side of the heart, left side of the heart, the right side with the deoxygenated blood. The blood comes out here. It goes off to the lungs, the alveoli at the lungs. It picks up oxygen, returns through the pulmonary veins back to the left side of the heart, then getting pumped out into the systemic circuit. Exchange occurs at the capillaries, and the stuff comes back through the venous system, back to the right side of the heart. Now, a lot of this stuff, this cardiovascular pathway, really going through the pulmonary circuit and systemic circuit, is nothing new. You guys have all seen this kind of thing before when you studied the cardiovascular system. Now, the only difference here then is these partial pressures of gases that are written all over the page. So I know there seems to be a lot of numbers here, but just let's take it step by step. And again, you'll find, I think, that it's not that bad. So let's start off with the inspired air. To make life simple, we're just going to go through oxygen. Just go through oxygen. So meaning all these PCO2s, you can completely ignore those for now. Eventually, you'll have to get some understanding of those, but for now, completely ignore PCO2s, and let's just look at the PO2s. All right, so let's get air into us. And so PO2 of inspired air is going to be 160. Now, where did that 160 come from? Well, again, we talked about this previously, and you know where it comes from. It comes from that partial pressure, this thing that we've looked at previously, right? We've looked at the partial pressure of oxygen, and we know that it's going to be 160. And the reason previously I rounded 159 to 160 was knowing that when I look at this slide here, they've also rounded 160. Okay, so the number is 160. How did it get there? If that doesn't make sense, go back and review information from that last lecture. Okay, so now the alveoli, the PO2 of the alveoli is 104. Now, right off the bat, you might have this thing of like, well, okay, why is it 104? What is making this thing 104? And I'm going to ask you just for now, just while we get through this, just to hold your horses. And for now, just believe me. Just accept that it's 104 and don't worry about how it gets to be 104 until a little bit later. Okay, we can address that. But for right now, just accept the fact that it's 104. All right. So you accept that, if you're working with me here and said, okay, I'll be patient, I'll understand some of the why a little bit later, then what? Fine, it's 104. I accept it. Now what? Well, which way does oxygen want to move? Does it want to move from atmosphere into lungs or lungs into atmosphere? Well, you see the way the PO2 is set up. The way the PO2 is set up, oxygen wants to move from inspired air into the lungs. So there we have it. Oxygen now comes into the lungs. Now, that is not to say that that whole thing about expanding the chest, thoracic cavity is no longer in play. Of course that's in play. All of this is kind of contextualized with that type of dynamic movement of the thoracic cavity. But again, this kind of average figure, we're going to say it's 104 right there at the lungs. Now, what do we need to do? We need to get that oxygen from the lungs into the blood, and that blood is coming right over here out. It's coming from the pulmonary arteries. This is your deoxygenated blood, and that deoxygenated blood is en route to the lungs. Now, the question that you have right off the bat is, what is the PO2 of the pulmonary arteries, right? You want to know what that is, and the answer here is 40. So again, your question might be, great, all right, 40, I guess I'll just memorize that it's 40. And for right now, until we can make some of the stuff make sense, just to allow me to get through this picture, yes, I just want you to assume that this is correct and it's 40. Just accept it for right now, okay? So if that's the case, the blood entering the alveolar capillaries or the pulmonary capillaries, the PO2 is 40. Which way is the gradient set up? Who's got higher partial pressure of oxygen? Obviously, it's the lungs. So which way does oxygen move? Does it go from the blood into the lungs or the lungs into the blood? Well, you know the answer. Oxygen moves according to a pressure gradient. So oxygen will go, it'll diffuse from the lungs into the capillaries. Now, how much of that will diffuse? How much oxygen is going to go from lungs into the blood? And the answer really is as much as it takes until there's no more gradient. And so what ends up happening is that we're going to top the thing off. So the blood leaving the alveolar capillaries is going to be 104. You got to ask yourself the question right now, well, could the blood leaving the alveolar capillaries ever be 105? Could it ever be 105? Let's exaggerate the point. Could it ever be 120? And right off the bat, you need to say, no, I don't think so. I don't think that PO2 leaving the alveolar capillaries could ever be 120. Because in order to get to 120, then that would mean that the partial pressure of oxygen in the lungs would have to be higher. But if you accept that it's 104, then you see that the maximum upper limit here is going to be 104 for the PO2 of the blood leaving the alveolar capillaries, because that's how diffusion works, right? Otherwise, if this is 104 and this is 120, then there must have been some active transport type of mechanism, which there isn't. This is all passive diffusion. So now what we see is the blood leaving the alveolar capillaries is 104, but the blood in the pulmonary veins is 100. All right, you need to have a little bit of cognitive dissonance here. You need to think to yourself, hang on a second, whoa. This textbook is showing me that the PO2 of the blood leaving the alveolar capillaries is 104, but in the pulmonary veins it's 100. But I could swear that in the cardiovascular system, we learned that exchange doesn't occur until you hit capillaries. So what is going on here? Where did the oxygen leak out? Was it consumed by the endothelial cells? Like, what is going on here? And here's what I think is a little bit poorly represented here, but I'm glad they did it so we can really make the point. Here's what ends up happening. Why is PO2 in the pulmonary veins less than the blood leaving the alveolar capillaries? Because this is just a sample. Really, the way these guys should have written this, it says in some parts of the alveoli, the blood leaving the alveolar capillaries is 104. In other parts of the lungs, those parts that are a little bit less well ventilated, the PO2 of that blood is like, let's say 98 or something like that. And so remember, when you look at the lungs, you've got the upper part, the middle part, the lower parts of the lungs, for example. As a general rule of thumb, the upper part of the lungs, the top parts, are not quite as well ventilated in a normal resting situation. So the blood leaving those parts of the lungs, the capillaries in those parts of the lungs, don't have quite as much oxygen. So this 100 is an average figure because they all dump together to form the pulmonary veins, right? All the blood leaving the alveolar capillaries from the base of the lungs might be 104. The blood leaving the alveolar capillaries from the apex of the lungs might be 100. And so therefore we average those things out and now we've got 100. Okay, great. There we are. Now, once we have the PO2 of the blood in the pulmonary veins at 100, here's my question. My question is, what is the PO2 of the blood at the left atrium, within the left atrium? It's not labeled, but pause the video and think it through. Same question. What is the PO2 at the left ventricle? What is the PO2 at the aorta? What is the PO2 in the systemic arteries? And so what you want to know is that you want to know that it is still 100. It's 100 because remember that exchange doesn't occur until you reach the capillaries. And that's true here with regard to oxygen as well, just as it was true for glucose or amino acids or whatever. Exchange occurs at the capillaries. So where does the PO2 initially drop? The PO2 actually initially drops at the tissues themselves. They're not going to drop. The PO2 in the systemic arteries and the arterioles are all going to be 100, okay, if all is going according to plan. So then now we're in the tissues. Now when you're in tissues, remember that this is the arterial end of the capillary and this over here is the venous end of the capillary. You got to remember those terms. And so what goes on? Well, the tissues themselves have a PO2 of 40 millimeters of mercury. 40. So now you're thinking 40. Hang on, man. I've seen that number 40 before. Where did I see that? The blood entering the alveolar capillaries was 40. That's where the number came from. That number 40 came from the tissues. The PO2 at the tissues is 40, meaning in the interstitium, in that interstitial fluid, there's oxygen dissolved within there en route to the tissues themselves. And the partial pressure of oxygen in that interstitial fluid is 40 millimeters of mercury. So what we're going to see, is there a gradient? Surely there is. 100 at the arterial end of the capillary, 40 in the tissues themselves. Of course, there's a gradient, so oxygen is going to leave the capillaries to enter into the tissues. All right? How much oxygen leaves? Well, as much as it takes until you no longer have a gradient. It's going to continue to dump oxygen until there is no more pressure gradient. And so then the PO2 of the blood leaving the capillaries is now 40. Again, one more time, where did that 40 come from? It came from the tissues. That continues to travel to the systemic veins. Is there any more exchange that occurs? Nope. Remember, exchange only occurs at the capillaries. So you go through at 40. So if I were to ask you, what is the PO2 of the blood at the right atrium? You should know the answer to that, even though it's not labeled on this picture. You should say, well, if the PO2 is 40 at the veins, and there's no more exchange happening, then I guess it's going to be 40 at the right atrium. You got it, and you're right. And same thing at the right ventricle. It's going to be 40. At the pulmonary artery, what's it going to be? It's going to be 40. And that's why the blood entering the alveolar capillaries, the PO2 was 40. All right? So what do we just do here? What we just did here is that we looked at oxygen. We traced a drop of oxygen coming in with a high partial pressure here. Okay, it's not the drop of oxygen doesn't have partial pressure. I'm saying the overall oxygen within the atmosphere, partial pressure is 160. There's a pressure gradient, so it easily goes in the lungs. There's a pressure gradient, so it goes in the alveolar capillaries. You know this diluting effect occurs, so some places are 104. I shouldn't say diluting, I should say an averaging effect. Some places the lungs are 104, other places might be like 95, 96, 97, whatever. And they all dump in together, so therefore the PO2 of the pulmonary veins is 100. Left atrium is 100. Left ventricle, PO2 is 100. At the aorta, PO2 is 100. At the systemic arteries, the PO2 is 100. Why? Because exchange hasn't occurred yet. It only occurs at capillaries. Once we enter in at the arterial end of the capillary, the PO2 is 100. You now see a pressure gradient. And now oxygen is going to leave to go into the tissues, as much oxygen as it takes until you reach a relative equilibrium, meaning a PO2 of 40, same as the tissues. And the reason you're not seeing the tissues climb, it's not going from 40 to 41 to 45 to 50 to 60 as you dump in oxygen, because it's one of those things. As oxygen comes into the interstitium, it immediately goes into the cells, and the cells are using that oxygen right away. Remember, we're not storing oxygen away. It's there. We use it immediately to make ATP. There is no storage form of oxygen. And so that's why it stays at a constant 40. If you've ever been around like a big family or a big group of people having dinner together, it's one of those things that the serving bowls always seem to be empty, because as soon as you fill the bowl up with spaghetti again, it disappears because people are eating it. And you fill it up with spaghetti again, you put it back on the table, and it disappears yet again. That's this tissue. It's very, very hungry. So it's going to maintain a relatively constant PO2 here of 40. Okay? All right. So this is what we see going all the way through. Please make sure you can work that through on your own. Now, the last thing that I'll say then is talk about this idea of PO2 in the lungs at 104. What I need you to see then, and this is kind of interesting, the expired air, the PO2 is 120. That's not going to make great sense right now in this lecture, but down the road, we're going to talk about this thing called dead space, and then the PO2 of expired air is going to make more sense. At the very least, for right now, what I want you to see then is that true or false, in the expired air, when you breathe out, there's oxygen in there. And the answer is, yeah, it's true. I mean, you got 120 millimeters of mercury of partial pressure of oxygen. So you definitely have air there. If you didn't have oxygen, I meant oxygen, not air. If you didn't have oxygen in that expired air, then, you know, when you're doing CPR, when you give those breaths, that component of CPR, not the chest compressions, then there would be no point in doing that, right? We're breathing in, presumably, because we want to give oxygen to the patient or the person who's down on the ground. Okay, so then what's up with 104? Here's what I need you to see with that 104. Look, there's constantly carbon dioxide diffusing in. That never stops. And I didn't go through the carbon dioxide. I'd encourage you to do that on your own. It is really, really important, but you should go through this carbon dioxide exchange as well. But there's constantly carbon dioxide coming in. So even though there's oxygen coming in and it's supposed to be nice and rich, it's constantly being diluted by this carbon dioxide. And so when you get those gases together, the fresh oxygen coming in, you would expect this thing to kind of top off at 160, but it doesn't, because we're constantly diffusing gas from the pulmonary capillaries back into the alveoli as well. When I say gas, I mean carbon dioxide, and therefore you're going to effectively dilute the PO2 to about 104. That's why this number 104 is there. And then why does it get enriched when it's in the expired air to 120? Why is it going from 104 to 120? And again, that explanation has to do with that dead space that we see in the lungs, which we won't get into right now. Okay, I've got two more slides here, and there's nothing new here. All this is showing you is at the lungs. If you zoom in, what's going to happen? There's the alveolus, there's oxygen. Oxygen is constantly diffusing into the pulmonary capillaries, and CO2 is diffusing out of the pulmonary capillaries back into the alveoli themselves. And there are the numbers right there. Okay, those numbers should be nothing new. And then at the tissues, what are we seeing? We're seeing that here's the capillary, there's the tissue cell. Oxygen is constantly diffusing from the capillaries into the tissues. And CO2 is constantly diffusing from the tissues into the capillaries themselves. Now, if you look at this, it looks like CO2 is going into the red blood cell. And you're thinking to yourself, whoa, hang on, red blood cells carry oxygen. But when I look at this picture, when I look at this picture, it kind of looks like that I'm dumping off oxygen, but I'm picking up CO2 on my return trip. And that's going to be the topic of another lecture, because that's absolutely correct. Those red blood cells will also carry and transport carbon dioxide. All right, so let's go and recap what we've covered. We looked at the PO2 of the inspired air at 160, of the alveoli at 104, at the pulmonary capillaries and then the pulmonary veins at 104, 100, right? When these things kind of hook up together. Systemic arteries, it's going to be 100. Capillaries, arterial vein is going to be 100. What's the PO2 of the tissues? Finally, we're at 40. Pressure gradient is there. Oxygen dumps out to the tissues. A whole bunch of oxygen dumps out so that the PO2 of the capillaries at the venous end are now going to be 40, and that's coming because it reached an equilibrium with the tissues. And then the PO2 of the systemic veins is also 40. So that should wrap it up for this video.